Greetings everyone, my name is Ruofei. I'm currently serving as the Interactive Perception and Graphics Lead at Google AR. Today, I'm thrilled to be here with you to share our latest research in Rapsai, accelerating machine learning prototyping of multimedia applications through visual programming. In recent years, there has been a rising number of real-time multimedia applications that leverage machine learning like 3D photos, portrait relighting, and virtual background in video conferences. However, prototyping ML-based multimedia applications is still challenging given complex workflows. Let's take portrait relighting pipeline in SIGCHI 2021 as an example. It consists of a geometry network, an albedo network, and a shading network, plus a body segmentation network to produce the final results. When testing with real-time video streams, there is no easy way to decouple the pipeline into individual components without significant amount of time encoding and slow communication among user experience researchers, application engineers, and ML researchers. In natural language research, rapid prototyping and evaluation of ML has gained recent attention with notable works like prompt chainer, AI chains, and tailbrush. Dating back to 1960s, visual programming has proved to be useful in helping users complete programming tasks. In graphics, node graph editor are also widely used for compositing complex rendering pipelines. However, all these existing tools can hardly satisfy the needs of machine learning practitioners in the multimedia domain, who often need to handle a lot of special purpose models such as face, body, and hand pose estimation, as well as scene or depth understanding, and dealing with video, graphics, and audio processing using OpenGL, Vulkan, and a lot of modern APIs. To better understand this space, we conducted a formative study with 7 computer vision researchers, audio ML researchers, and engineers through semi-structured interview and a mock-up sketch of our envisioned system. We identified 6 challenges from the formative study, starting with lack of data processing for input in the wild, lack of interactive data and model tuning, loss of application context, lack of direct comparison and sharing, slow iterations, insufficient controllability. This study helped us derive 6 design goals, which informed Rapsai, a visual programming platform for rapid and iterative development of end-to-end ML-based multimedia applications. First, provide a visual programming platform for rapidly building ML prototypes. Second, we want to support real-time multimedia user input in the wild. Third, provide interactive data augmentation. And fourth, compare model outputs and render results directly side by side. Fifth, share visualization with minimum efforts. And finally, we aim to provide off-the-shelf models and datasets. Next, let's watch a quick video of the Rapsai system, starting from building a multimedia pipeline from scratch, using an image node, body segmentation node, shader processing, and a background image, and blending these 2 images in real time. And finally, we use a live camera node to test the pipeline in real time. And here is another example of changing the blurring kernel in the virtual background. In another demo, we compare 2 scene depth models side by side and using different interactive data augmentation techniques. And here, using the comparison, we can directly output the figure that we want to use in our presentation. We designed Rapsai iteratively over a year with weekly feedbacks from 3 ML teams. Rapsai is a cross-platform application that operates within a web browser, leveraging technologies including TensorFlow.js, 3.js, and WebGL. Its final design consists of 4 panels. First, node library contains 5 types of nodes, with 37 in total in our paper appendix, and a search bar to filter desired nodes. Our node graph editor allows users to build and adjust a multimedia pipeline by dragging and dropping nodes from the nodes library, or suggesting available nodes when dragging an edge from an existing node. The preview panel depicts visualization of every visible node in the node graph editor. One of my favorite visualizations in Rapsai is this interactive data augmentation, which enables ML practitioners to quickly generate side-by-side comparison of a wide range of data augmentation techniques with any input image or video in the wild. The last panel, Node Inspector, shows advanced properties of a selected node. For example, users can upload their own images for rapid testing when selecting an input image node. One very cool feature was its shader library. Our shader effect nodes allows users to choose a predefined shader from a library of over 50 visual effects or write their own fragment shaders using GLSL. To evaluate the usability and effectiveness of Rapsai, we conducted 4 case studies with 15 ML practitioners. These cases are portrait depth with relighting effects, scene depth with fog effects, alpha matting for virtual background, and audio denoising for remote communication. Each case study consists of 5 stages: a background interview, a video tutorial, a visual analytics, a discussion, and an exit survey. Overall, when comparing with mature coding tools that ML practitioners often use for prototyping like Colab, they find Rapsai less controllable, but more transparent and collaborative. For example, practitioners can accelerate their workflow, reducing their prototyping time from 1 hour to a few minutes. Furthermore, Rapsai can assist in identifying issues with ML models and training sets. For example, P10 found a significant performance issue with the contrast slider and realized that this issue could be fixed by increasing the receptive field. Another participant found that I can manipulate the brightness to see when the model fails. Rapsai can further identify biased augmentation of the training sets, holistically evaluate model behavior with real-world input, or help determine whether more training data is required. Finally, Rapsai helps model selection, learning from pipelines, and study deployment. For example, it provides qualitative evidence to select the optimal model, or assist in sharing qualitative findings in presentations and publications, or assist novice prototyping practitioners to learn how to build a multimedia pipeline. In conclusion, Rapsai lowers the barriers for the development of ML-based multimedia applications. It empowers users to experiment with different ideas and designs without worrying about coding or technical details. It also facilitates collaboration between designers and developers by providing a common language for describing ML pipelines by sharing the webpage ethically. In the future, we plan to extend the framework to support text and 3D data, and integrate more closely with the training pipeline and cloud-based models. Our team is also working on launching Rapsai with publicly available models. Stay tuned for our announcement. And we firmly believe that With the right tools, everyone can unleash your inner creativity. Thank you everyone for watching. Any questions are welcome.